So En actually is the expectation value of the Hamiltonian, if you want to do. Just, I mentioned that here, but I don't use too much from this information. Just multiply that to the psi n and make the integral, so you will get this expression. So this is the expectation value of Hamiltonian, and this is normally 1 if your function are wave function are normalized. Integral of psi squared, we set 1. So En is the expectation value of Hamiltonian in some special basis. So you needed to fix your psi n. It's called basis. One more thing is that each Hamiltonian can be written in the matrix form. So always it's possible to consider this H psi n as that. This is a Schrödinger picture. Yes? And writing the matrix form is the Heisenberg picture. In Heisenberg picture, instead of these, you will work with the matrix. So H11, H12, H1n, H21, H22, Yes, that's the Hamiltonian. I want to tell you that H11 is E1, and this is E2, and this is the element with the diagonal element, actually, MM is EM. For this information about that. So this equation is this. Yeah. So just this is another alternative method to find Q1, and you see that will work with Hamiltonian. So how I write E minus beta E1? So can I write that like psi 1 E minus beta H psi 1 psi 2 for the next one, E minus beta H psi 2 psi m E minus beta H psi m. Why? Why? Because of this equation. H psi m is E n psi m. Exponential of H psi 1 is E minus beta E1 psi 1. Yes? And this is a E minus beta E2 psi 2. And this. Okay. So tell me what is that? So this is it looks like the first, the diagonal element of this, diagonal element of this, diagonal. So can I write this sigma n psi n E minus beta H psi n. I want to write that trace E minus beta H. Trace. Trace means the elements, the summation of the element over the diagonal. Just this. Add. Summation over whole diagonal element. Okay. So An alternative way to find that, but I don't solve the example by this method because it takes time, so it will be for the next lecture. Just I show you for you that Q1 beta, which is given E minus beta En for one particle, can be reduced to the trace operator minus beta H also. Let's go and try just take the particle in the box. So particle in one-dimensional box. So this is the Schrödinger equation. As you know, one-dimensional system. If you solve the system, so psi 0 will be psi L. So the energy state will be n squared, p squared, h squared, 2ml squared, n is from 1 to 3. This is the energy state. But try to find the Q from here. Look what happened. Oh, you get something like that. Can I write this? I don't know. Some new parameter. We call it beta dash. Any parameter. Yes. Any parameter. We need to sigma minus beta n squared. So there is no any simple way to find that. If it was E minus beta n, I calculated what was the, you know how was that 1 minus E minus beta was. But for n squared, no. So I will ask you to go and find analytic form for this series. I mean, what is that? Like here, it will be minus. Find it that, so you will get something called a theta function, Jacobi function. That is just I give you as a hint that hint is that it reduced to Jacobi's function, and that's it. But do that and go and find the, because you know how they treat this example in textbooks. They write up to here. After they say that, not all the books, of course. They say that it's not easy to find this, so we pass to the two limits. You know what's the limit? High temperature and low temperature. In high temperature and low temperature, you can find this series. But I want the exact one. I want the exact partition function of the system. If you find for me the Q1, you know you will have the Qn, Q1 beta power n factorial, and after that you can find entropy and everything. So that will be a quantum particle in the finite temperature in the box. Still you see that we cross the Schrödinger equation. We use this Schrödinger equation is valid only at, several times I told you, Schrödinger equation working only in the pure quantum mechanical case, so means when t is 0. When t is not 0, we use this. We use the solution for the t0, but we use the concept of partition functions. We give the weight to the state with the non-zero